Hello and welcome. It's truly good to have you here. Today we're going to rely on scientific evidence to understand a process of truly colossal scale. Have you ever paused to consider what is really happening inside the sun and how its energy is actually produced and transported? According to our current theoretical models, the sun remains stable because of an internal balance that is astonishingly delicate. Would you believe me if I told you that the light touching us today may have been created when human beings had not yet mastered agriculture? According to the physical models of the solar interior, that energy can spend thousands of years traveling through dense plasma before it finally escapes. Along this path, we will follow the birth of the sun and the conditions that allowed this star to exist. We will move inward through its structure, crossing its layers until we reach the core. We will trace the journey of energy inside the sun until the moment when light finally arrives here. We will observe how this energy sustains life and maintains the balance of our planetary system. And we will also move forward in time to understand what the ultimate fate of the sun will be and the legacy its light will leave behind. But before we continue, I'd like to ask for a small moment of your support. If you enjoy calm explorations of science like this one, consider subscribing, leaving a like, and sharing this journey with someone who might also appreciate it. Simple gestures like these help the work of Cosmos for Rest continue reaching curious minds who enjoy learning while they unwind. Now allow your body to relax. Close your eyes, and let the science gently guide the way. To begin our journey through knowledge, we first need to understand that the silence of space is not the same as an absolute emptiness or the absence of future life. Before our solar system existed, before even the first particle of light from this stellar engine could touch what would one day become the ground of our future home, there was only a vastness, cold, silent, and seemingly eternal. Can you imagine the scale of a cloud drifting through darkness, carrying within it the weight and the destiny of trillions of future worlds? That was our most distant origin, a structure science describes as a giant molecular cloud, composed mostly of hydrogen and a small portion of helium, elements left behind from cosmic events even older and more violent that occurred in distant ages of the universe. In that primordial era of darkness, temperatures within this cloud were extraordinarily low, approaching what we know as absolute zero, around -273 degrees Celsius. It might seem almost impossible that something so cold, so dispersed and so nearly immaterial could transform into the colossal furnace that now keeps us alive and warms our days. The beginning of that transformation did not come from a sudden explosion, but from something more subtle, a gravitational whisper, almost imperceptible. According to cosmological studies, an external disturbance, perhaps caused by the shockwave of a distant star reaching the end of its life, traveled through the vacuum until it encountered our cloud. That small vibration became the trigger that allowed gravity, this invisible force that pulls everything together, to begin its quiet work upon the primordial matter. As gravity slowly overcame the natural thermal resistance of the gas, the cloud began to experience what scientists call gravitational collapse. Can you almost feel the pressure increasing as trillions of tiny particles of dust and gas are squeezed into an ever smaller region by an inescapable embrace? This process is a perfect example of energy transformation, where gravitational potential energy begins converting into heat. The cloud, once a cold and static stain in the firmament, started warming at its center, creating what science defines as a protostar. This central object was not yet a true star, because nuclear fire had not ignited, but it already possessed a monumental mass that dictated the rhythm of everything around it. You might find it astonishing that because of the law of conservation of angular momentum, all that collapsing mass began spinning faster and faster. Imagine a ballerina drawing in her arms to rotate more quickly around her axis. That is exactly what happened to our sun in formation. This rotational motion flattened the surrounding cloud into a vast, thin structure known as a protoplanetary disk, while the central core continued growing with relentless hunger, pulling toward itself most of the available matter. It is fascinating to realize how order began emerging from what once seemed like absolute chaos, where a swirling storm of incandescent plasma and dust gradually organized the foundations of what would become our home in the universe. As we continue imagining this early environment, we notice that the young sun struggled intensely to stabilize itself amid the conflict of monumental forces. There was a constant battle between gravity, which tried to crush all matter into a single infinitely small point, and the thermal pressure of heated gas, which pushed everything outward. For hundreds of thousands of years, gravity held the advantage, compressing the plasma core until the density became so high that hydrogen nuclei had nowhere left to escape. Can you imagine the weight of 333,000 Earths concentrated inside a blazing sphere? That was the state of our sun before its first true breath of light, an opaque sphere holding heat within itself, like a secret guarded by the very laws of physics. At this protostellar stage, the temperature at the center rose from just a few degrees above absolute zero to thousands of degrees Celsius, in a period that, on the scale of cosmic time, was only a brief transitional moment. The matter inside no longer behaved like the gas we breathe, but instead like a dense, agitated plasma, where electrons were stripped from their atomic nuclei by the violence of the heat. It may seem incredible to realize that the young sun passed through a phase of extreme turbulence, ejecting jets of matter from its poles and clearing the surrounding disk through powerful stellar winds. This cleansing process was essential for the formation of planets from the dust that remained after the central giant had claimed most of the available material. For the true transformation to occur, the core had to reach a critical point of temperature and pressure that challenges everyday intuition. Scientific theory tells us that when the temperature approaches 10 million degrees Celsius, hydrogen nuclei finally overcome their natural electrical repulsion. Imagine these nuclei as tiny spheres that refuse to touch one another, but under the colossal pressure of solar gravity, they are forced together in an event known as nuclear fusion. This moment marks the true birth of a star. When the first hydrogen atoms fused to form helium, an unimaginable amount of energy was released in the form of photons and neutrinos, marking the beginning of the sun's stable life in what astronomers call the main sequence. Can you sense how monumental this balance is for our existence today? If the original gas cloud had possessed just a little less mass, the sun would never have ignited this internal fire and would have become a brown dwarf, a failed star that never shines with full intensity. But our cloud was generous, containing exactly the right amount of matter to create a stable and long-lived star. That birth was not merely an isolated astronomical event, it was the foundation of the entire biological system we know today. We still feel the consequences of that beginning in every beat of our hearts, because many of the chemical elements that compose our bodies were forged or assembled during these very processes of stellar formation. Across millions of years, the sun transformed from a hidden promise in the cold darkness of space into the gravitational ruler of our system. The light that now touches our skin is the final outcome of a story that began with the simple collapse of a cloud of dust. You might find it remarkable how patient the universe can be when building something so complex from such simple components. It is a story of physical persistence, where gravity sculpted light out of the deepest darkness. And it is important to remember that this journey of formation is shared by nearly every star we see in the night sky, each one passing through this same ritual of pressure, heat, and birth. When we discover how the sun was born, we realize that we ourselves are made of the same matter that once drifted inside that primordial cloud. Every atom of oxygen we breathe, and every trace of iron flowing through our blood, once participated in that turbulent creation. The birth of the sun was the opening act of a cosmic performance that has already lasted 4,500,000,000 years, and will continue for a very long time yet. There is something comforting in knowing that the light sustaining us has roots so deep in cosmic history, and that science allows us to reconstruct these steps with remarkable precision, letting our minds travel from the cold of absolute darkness to the radiant warmth of our star. The engine ignited in the center of that molecular cloud is the same engine that ensures time continues to flow for us. Now that we understand how this immense mass of plasma organized itself and took its first steps in the cosmos, we can begin to dive even deeper into its invisible anatomy. The birth of the sun was only the beginning of a complex structure, where each layer plays a vital role in transporting the energy generated in the heart of the star. As we continue this exploration, we will move through the details of this stellar body, sensing how pressure and temperature change dramatically as we approach the center. The sun is not simply a uniform ball of fire, but a physical organism composed of distinct layers and specific functions that ultimately allow light to escape into space. Now that we've moved across the outer layers and felt the crushing weight of the sun's structure, I invite you to sink into the deepest and most sacred point of this star. We arrive at the core, the true engine of existence, where time and matter behave in ways that completely defy the logic of our everyday experience on Earth. Can you imagine a place where the temperature reaches 15 million degrees Celsius and the pressure is so immense that the very distinction between atoms begins to dissolve. This is the heart of the sun, an invisible furnace operating in absolute, monumental silence, creating the light that, thousands of years from now, will touch our face on a spring morning. Here, the fate of the solar system is decided every fraction of a second through a subatomic dance that would seem unbelievable if not for the precision of mathematical models and the evidence modern science provides. In this environment of extreme density, matter exists as plasma so compressed that hydrogen nuclei, essentially lone protons, are packed tightly against one another. Under ordinary conditions, these protons repel each other with enormous force because they carry the same positive electric charge, like two identical poles of powerful magnets refusing to make contact. It can be surprising to realize that even at 15 million degrees, thermal agitation still wouldn't be enough to overcome that natural repulsion. If we relied only on classical physics, the sun would never have ignited. And yet the universe keeps a subtle mechanism hidden in the deeper layers of reality: quantum tunneling. Through this small opening in the laws of probability, a proton can occasionally slip through the invisible barrier and touch its neighbor, triggering the chain of reactions that sustains all life. Can you feel the impact of that union? When two protons finally fuse, they begin what we call the proton-proton chain. The first step involves a profound transformation. One proton converts into a neutron, emitting a positron and a neutrino in the process. This union forms a deuterium nucleus, a heavy form of hydrogen. It is a slow and unlikely journey. For an individual proton, the probability of undergoing this fusion is so small that it could drift through the solar core for about 9 billion years before the event occurred. But because the sun contains an amount of hydrogen that stretches the imagination, this event happens trillions of times per second throughout the core. The star's monumental scale compensates for the rarity, ensuring the flow of energy remains constant and unshakable. After deuterium is created, the dance becomes faster and more intense. A third proton collides with this newly formed nucleus, fusing with it and creating a helium-3 nucleus. In that instant, a tremendous amount of energy is released as gamma radiation, the most energetic form of light we know. At that moment, energy stops being merely potential and becomes a radiant force that begins its long journey outward from the core. But the process still isn't complete. Two helium-3 nuclei must meet and collide, fusing to form a stable helium-4 nucleus, and releasing two protons back into the plasma, ready to restart the entire cycle. It is an almost perfect recycling system, where matter is continuously transformed under the steady watch of gravity. But where does all that energy come from? The energy we feel on our skin millions of kilometers away? The secret lies in a small, almost imperceptible loss of mass. It may seem incredible to notice that the resulting helium nucleus is about 0.7% lighter than the 4 protons that began the process. That mass did not vanish into nothingness. It was converted directly into pure energy, following the famous relation that energy equals mass, multiplied by the square of the speed of light. And because the speed of light is such a gigantic number, a tiny amount of matter can produce an extraordinary release of energy. Every second, the sun converts roughly 600 million tons of hydrogen into helium, and in that process, about 4 million tons of mass becomes pure light and heat. It is a scale of transformation so immense that it has sustained the star's brilliance for billions of years. Can you imagine what would happen if this atomic engine ran without any control at all? The reason the sun doesn't explode like a gigantic hydrogen bomb is the balance we mentioned before. Nuclear fusion in the core is extremely sensitive to temperature. If the fusion rate increases, the core heats up and expands slightly against gravity. That expansion spreads the atoms apart, reducing the likelihood of further fusions and letting the temperature fall again. If the core cools, gravity compresses it once more, increasing pressure and reigniting the nuclear reactions. It is a stellar thermostat of astonishing precision, keeping the sun's brightness nearly constant for billions of years and allowing life on Earth to evolve slowly and steadily. While photons begin their tortuous journey through the star's upper layers, there is a particle that escapes this burning heart almost instantly. These are neutrinos, the near-ghost particles of physics. It can be surprising to know that right now, trillions of solar neutrinos are passing through your body, your home, and the entire planet Earth every second, moving essentially at the speed of light. Because they barely interact with matter, they can escape the sun's core in just 2 seconds and travel straight through space until they reach us. By capturing these particles in extremely sensitive underground detectors, scientists can indirectly observe what is happening inside the sun, confirming that the fusion engine remains active. To feel the rhythm of the solar core is to understand the origin of complexity in the universe itself. Without this fusion process, the cosmos would be dark, cold, and stripped of any elaborate structure. Every helium atom formed in the sun's center is a testament to the strong nuclear force, the fundamental force that binds nuclei together against near impossible odds. The energy that now begins to move through solar plasma will be the same energy that feeds plants, drives air currents, and keeps Earth's water cycle in motion. There is a deep connection between that small, dense core, hidden beneath hundreds of thousands of kilometers of plasma, and the simplest gestures of human life. Science reveals the sun as a system that finds stability through extreme conflict. The core is a battlefield where heat tries to tear matter apart while gravity tries to draw it together. From that struggle emerges the steadiness we call daylight. Imagine billions of atmospheres pressing on every fragment of matter, turning gas into something denser than lead, and yet still fluid, like an invisible ocean. It is a reality that challenges our senses and invites a deep humility before the grandeur of stellar mechanisms. The heart of the sun is, in the end, a symbol of transformation, where mass slowly sacrifices itself to become light. To reflect on nuclear fusion is to realize that energy isn't something the sun simply possesses. It is something the sun continuously creates through a colossal effort. Every photon that will eventually escape into space will be the survivor of a long journey that began in this burning center, where quantum physics and relativity coexist in an extraordinary balance. It may seem surprising, but the sun has already consumed roughly half of the hydrogen available in its core, and still, the remaining reserve is enough to sustain this process for about another 5 billion years. The solar engine is in full maturity, operating with an efficiency no human technology could ever match. In this passage through the heart of the star, we discover that light is not merely brightness. It is the result of a silent subatomic struggle that happens unceasingly inside matter. The sun turns mass into energy, and energy into life. As we close our eyes and imagine that incandescent center, we feel the presence of a universe that organizes itself to produce warmth in the midst of cosmic darkness. Let's carry with us this understanding of pure energy and the invisible effort that holds the firmament together. The calm light that enters through the window is, in truth, the distant echo of a nuclear roar that continues, without pause, in the heart of our star. Now that we understand the miracle of nuclear fusion unfolding in the burning heart of our star, I invite you to follow what may be the longest, most patient journey in the entire story of our solar system. Imagine the birth of a single photon, a particle of pure and intense light, created during those violent collisions we just explored inside the core. At the moment of its creation, this photon exists as extremely energetic radiation, a gamma ray, carrying within it the promise of illuminating a distant world one day, and yet it cannot simply fly away. Can you imagine what it would be like to be the fastest thing in the universe, and still find yourself trapped in a labyrinth so dense that every step forward demands countless detours? This is the odyssey of light, a journey so astonishing that the sunlight touching your face this morning may have begun its path tens or even hundreds of thousands of years ago. Leaving the nuclear furnace at the center, the photon enters a region scientists call the radiative zone. This is where the odyssey truly becomes a test of patience. It may surprise you to realize that although light travels at 300,000 kilometers per second in the vacuum of space, inside this solar layer, it struggles to move even a few millimeters at a time. The plasma in the radiative zone is so compressed, so crowded with atomic nuclei and free electrons, that our small traveler cannot move in a straight line for more than a tiny fraction of a second. It collides, is absorbed, is re-emitted, and is scattered in every possible direction. Imagine this motion as a random walk, where for every step the photon takes toward freedom, it is pushed sideways, or even back toward the core, from which it came. This immense density turns the sun's interior into something almost impossible to imagine for a gas. It becomes a labyrinth of opaque mirrors where light is constantly captured by matter. Can you feel the patience required for such a journey? If the sun were empty space, light would take just over 2 seconds to cross its radius, and escape into the cosmos. But because of this extraordinary density, the photon remains imprisoned for a time that challenges our sense of history. Scientific estimates suggest that the light we see today may have been created in the solar core more than 170,000 years ago. That means while early humans were still shaping their first primitive tools on Earth, this exact packet of energy had already begun its struggle through the sun's plasma. It can feel almost unbelievable to realize that sunlight is, in a way, a fossil of energy from a time long before our civilization. As the photon wanders through the radiative zone, it doesn't only fight distance, it also undergoes a profound transformation. When it was born in the core, it existed as a gamma ray, a type of radiation so powerful that it would be lethal to life if it reached Earth directly. But through trillions upon trillions of collisions, the photon gradually loses energy. Each time it is absorbed by an electron and then emitted again, it becomes slightly less energetic, shifting its wavelength step by step through the invisible spectrum. First it softens into X-rays, then into ultraviolet radiation, and eventually, by the time it approaches the outer layers, it reaches the frequencies of visible light that our eyes can perceive. In this long journey, the fierce violence of the solar core is slowly transformed into the gentle warmth and brightness that sustains photosynthesis and life. It is astonishing how nature performs such a precise adjustment, turning the fury of nuclear reactions into a light soft enough to nourish a leaf. In this slow passage, time begins to lose the meaning we usually assign to it. Imagine an environment where there is no day and no night, only a diffuse glow and a pressure that crushes the very idea of empty space. You might picture the photon as a message sent from an ancient past, carrying with it the memory of the fusion reaction that created it. For millennia, it drifts through this sea of plasma, bounced from side to side by restless electrons. The radiative zone occupies almost 70% of the sun's interior path, and it is here that the photon spends the vast majority of its existence. It is a quiet lesson in persistence. Even light, the swiftest entity in nature, must struggle patiently to escape the grip of dense matter. It can feel remarkable to think that the sunlight that once illuminated the pyramids of Egypt or the cathedrals of medieval Europe may already have been halfway through its journey inside the sun, long before those structures were ever imagined. In this sense, the sun becomes a vast reservoir of time. What we see now is not what is happening in the core at this exact moment, but rather the echo of an ancient process slowly reaching us. This understanding changes how we experience the warmth of daylight. It is not an immediate event. It is a gift prepared and sent long ago, traveling patiently through barriers no other force could overcome. Every ray of sunlight carries the weight of cosmic history and the calm patience of a universe that never rushes its creations. As the photon finally approaches the boundary of the radiative zone, the temperature and density begin to decrease slightly. It senses that the resistance is weakening, but the journey is not over yet. Ahead lies a region where the rules of energy transport will change completely. Before reaching that place, however, we pause to appreciate the endurance of this photon. Can you imagine the solitude of a particle that, for 100,000 years, has never seen open space or the vacuum of the cosmos? It has lived entirely within the embrace of solar plasma, a part of the star itself, until its energy softened enough for the next stage. This long odyssey is what prevents the sun from releasing all its energy at once. If the interior of the star were transparent, nuclear fusion would consume hydrogen at a catastrophic speed, and the sun would burn brilliantly for only a short time before collapsing. It is precisely this difficulty, the labyrinth of the radiative zone, that regulates the flow of energy. It holds the heat, releasing it gradually and patiently, ensuring the star shines for 10 billion years rather than only a few million. In an almost paradoxical way, the inefficiency of light's escape becomes the reason life has had enough time to flourish on Earth. Following the journey of a photon invites us to rethink how we perceive time and importance. We often imagine that the fastest things matter most, yet the sun quietly teaches that the foundations of life are built by slow, persistent processes. Sunlight itself is evidence of eternity operating in the present moment. When you feel warmth on your hands, you are touching energy that began its journey in a world that was profoundly different from ours. It is a direct connection to the ancient interior of our star, an unbroken thread of light linking distant ages through dense plasma. Now the surviving photon approaches the next region of the sun, where its lonely wandering will end. Instead of drifting randomly between particles, it will be carried upward by enormous movements of matter, vast bubbles of plasma rising like elevators of fire. After crawling across hundreds of thousands of kilometers step by step, the photon is finally nearing the possibility of freedom. Its energy, now softened into visible light and gentle warmth, is ready for the final stages of its journey toward our world. Keep this image in your mind: a small point of light, persistent and patient, never giving up its search for a path outward despite countless collisions and endless centuries of wandering. This is the nature of the light that surrounds us. It is a traveler through time, a survivor of an immense cosmic struggle that ended in the quiet moment when we open our eyes and see the world around us. The sun, above all, is a storyteller made of light, and every day is a new page in that ancient odyssey that began in silence deep within its core. Now that we have followed the silent, millennia-long odyssey of the photon through the dense radiative zone, I invite you to feel a dramatic change in the rhythm and character of our stellar journey. Imagine that after wandering for hundreds of thousands of years through a labyrinth of microscopic collisions, the energy finally reaches a region where the rules of the game transform completely. We are entering the convective zone, the outermost layer of the sun's interior, occupying the final 30% of the path toward the surface. Here, the plasma is no longer as tightly compressed, and although the temperature is still immense, it has dropped enough that pure radiation can no longer carry energy efficiently. Can you imagine what happens when light encounters a barrier of opaque matter? It is as if the sun decides that, to move heat forward, it is no longer enough to pass energy quietly between atoms. Now the star must move the matter itself, in a colossal dance of fire and motion. And it can feel astonishing to realize that we are about to step into a monumental elevator of plasma, where bubbles of fire the size of continents rise and fall in an eternal cycle. At this stage, solar matter behaves in a way very similar to water boiling in a pot, forgotten on the stove in a quiet kitchen. Can you sense that familiar image? At the bottom of the convective zone, plasma is heated by the radiative region beneath it, becoming less dense and more buoyant. Obeying the fundamental laws of thermodynamics, this superheated plasma begins to rise, tearing upward through the depths toward the surface. The scale of this motion is difficult to grasp. We are not speaking of small bubbles of air, but of enormous columns of incandescent plasma, traveling distances of 200,000 kilometers. It is an ocean of fire in constant motion, where each convective cell acts like a gear in a vast thermal engine that keeps our solar system alive. Feeling the pulse of this motion is like sensing the raw force the sun uses to distribute its vitality throughout the cosmos. When we picture these rising bubbles, we begin to understand the magnitude of what is happening. Some of the largest structures, known as supergranules, can reach diameters of 30,000 kilometers, more than twice the size of Earth itself. Imagine a single bubble of blazing plasma, capable of swallowing our planet without effort, rising through the solar interior at speeds of hundreds of meters per second. It is a display of power that makes us feel small, yet also deeply connected to this celestial mechanism. This movement of matter ensures that the energy created in the core does not remain trapped in the depths, but is delivered steadily and vigorously toward the outer layers, where it will finally become the light that brightens our days. Inside the convective zone, the transport of heat becomes far faster than in the radiative region below. While a photon required tens or hundreds of thousands of years to cross the earlier layer, here the rising plasma can complete its journey in only a few weeks. Can you sense the relief in this sudden acceleration? It is as though the star is finally breathing, releasing the heat stored within through immense currents of plasma. When these rising bubbles reach the top of the convective zone, they release their energy and cool down, becoming denser once again. Then they sink back toward the depths, where they will be reheated and rise again. The downward motion happens in the spaces between the rising columns, forming a complex and turbulent network of flows that keeps the sun in a constant state of restless movement. The internal traffic of heat rising and cooler material descending is astonishing in its complexity. The turbulence of this layer does more than transport heat. It also gives birth to one of the most powerful invisible forces shaping our solar system: magnetism. Can you imagine how the motion of electrically charged plasma, combined with rotation, can generate enormous magnetic fields? This process, known as the solar dynamo, takes place within the convective currents. As plasma flows, it stretches, twists, and wraps magnetic field lines around itself, transforming the energy of motion into magnetic energy. It can be surprising to realize that the same bubbles transporting heat are also responsible for creating solar storms and the dark sunspots that occasionally appear across the sun's surface. Thermal physics and magnetic physics intertwine here, creating a complex symphony that determines the temperament of our star. If we could touch the sun's surface, we would feel the texture of this convection as a pattern of glowing granules. Imagine the solar surface as a vast quilt stitched together from boiling cells of plasma. Each bright granule represents a rising bubble of hot material, and each darker boundary marks where cooler plasma sinks downward. These granules live for only a few minutes before disappearing and being replaced by new ones rising from below. It is a constant renewal, repeating endlessly for billions of years. The convective zone forms the final interface between the mysterious interior of the sun and the open space beyond, acting like a massive radiator, preparing the energy for its final release into the cosmos. If sound could travel through the vacuum of space, the boiling ocean of plasma inside the sun would produce an immense, continuous roar, a deep cosmic hum created by trillions of tons of matter colliding and moving in turbulent currents. Although space itself is silent, the sun vibrates like a gigantic bell. Scientists study these vibrations through a field known as helioseismology, allowing them to listen to the internal structure of the star. By observing tiny oscillations on the solar surface, researchers can infer the speed of internal flows and the strength of magnetic fields hidden deep within. Through the rhythm of convection, the sun quietly reveals its secrets. The importance of the convective zone reaches far beyond the transport of heat. This region also mixes the sun's chemical elements, ensuring that its plasma remains relatively uniform throughout. In addition, the energy carried upward by these currents feeds the outer solar atmosphere and powers the solar wind that spreads across the entire solar system. Even our modern technology feels the influence of these processes. The magnetic disturbances born here can affect satellites, radio communication, and electrical systems on Earth. It is astonishing to realize that movements occurring hundreds of thousands of kilometers inside the sun can influence everyday life on our planet. As we continue this mental journey, the convective zone reveals itself as the place where brute force becomes organized motion. It marks the transition from the silent density of the core to the vibrant activity of the solar surface. Each rising bubble of plasma carries a message from the nuclear furnace deep below, announcing that fusion continues successfully in the heart of the star. When we imagine this layer, we feel energy itself preparing for liberation, transforming from trapped heat into the light that will soon escape into space. Keep this image with you, an immense elevator of fire, lifting energy toward freedom. The grandeur of this process unfolds on a scale almost beyond imagination. The convective zone is the final great barrier before the light escapes, a turbulent ocean through which energy must travel before it can leap into the vacuum of space. Here we feel the sun's pulse in its most mechanical and dynamic form, and from this boiling sea of plasma, the warmth we feel on Earth is ultimately delivered, carried upward by colossal cells of fire working tirelessly in the depths of our star. After the colossal turbulence of plasma bubbles within the convective zone, we finally arrive at the last boundary, the delicate threshold where matter releases light and allows it to fulfill its destiny. Imagine that after thousands of years imprisoned in the dense depths of the sun, our surviving photon reaches a region so thin and subtle that the physics itself begins to change. We have reached the photosphere, the golden layer we usually think of as the surface of the sun. Yet there's nothing solid there. It is only a glowing mist of incandescent gas, a place where density falls so dramatically that plasma ceases to be an opaque maze and becomes transparent enough for light to escape. Can you feel the lightness of this moment? It is the instant of liberation. The photon that was born in the furnace of the core and endured trillions of collisions now discovers that nothing stands in its way. For the first time in hundreds of thousands of years, it can finally travel in a straight line. In this thin layer, the temperature settles around 6,000 degrees Celsius. Compared with the millions of degrees in the sun's interior, this might sound almost gentle. Yet it is precisely the right temperature for radiation to emerge as the visible spectrum that warms and illuminates life. It can be surprising to realize that the photosphere is only about 500 kilometers thick, an almost negligible skin compared with the immense radius of the star itself. It is like a luminous veil covering a giant furnace beneath. The moment our photon crosses this boundary, it ceases to belong to the sun and becomes a traveler of open space. The contrast is extraordinary. Behind it lies the roaring turbulence of plasma and crushing pressure. Ahead of it lies the silent vacuum of the solar system. Free at last from the dense grip of matter, the photon moves at the maximum speed permitted by nature, 300,000 kilometers per second. Imagine what that speed truly means. In a single second, light can circle the Earth more than 7 times. Yet the universe is so vast that even this astonishing velocity requires time to bridge the distance between the sun and our world. Between the star and the Earth stretches an immense emptiness of about 150 million kilometers. The photon begins its silent crossing. It passes the orbit of Mercury, gliding above the scorched and airless landscape of that small world. Then it continues outward, sweeping past the thick and acidic clouds of Venus. Always moving forward, always in a straight line, it follows the same path traveled by countless trillions of companions. Together they form what we perceive as sunlight, a river of radiant energy flowing continuously through space. This voyage across the vacuum lasts exactly 8 minutes and 20 seconds. In cosmic terms, it is a brief and effortless sprint compared with the millennia the photon spent inside the sun. And yet, during these few minutes, the light moves through perfect purity. Nothing absorbs it. Nothing redirects it. It simply exists, racing through the darkness. It can feel almost unbelievable to realize that the sunlight reaching the top of Earth's atmosphere may have begun its long escape from the solar interior when mammoths still roamed icy landscapes. The light we feel today is not merely current energy. It is a messenger from the ancient past of our star. As the photon approaches Earth, it encounters its first obstacle since leaving the sun, our planet's atmosphere. After traveling through pure vacuum, the light suddenly plunges into a sea of gas composed mostly of nitrogen and oxygen. Here, another transformation occurs. Molecules of air scatter the shorter blue wavelengths of sunlight in every direction, painting the sky above us in its familiar blue dome. Without this scattering, the daytime sky would appear black, even under the full brilliance of the sun. The atmosphere also performs another essential task. It acts as a protective filter, absorbing the most dangerous forms of radiation while allowing visible light and gentle warmth to reach the ground. This thin layer of gases turns the raw energy of the sun into something safe enough to nourish life. The photon that endured so many collisions within the sun now begins to interact with clouds, oceans, forests, and mountains. Eventually, after traveling 150 million kilometers, the photon reaches its final destination in a place that might seem astonishingly simple: the human eye. Imagine the particle of light entering through the cornea, passing the pupil, and being focused by the lens onto the retina at the back of the eye. There, inside a thin layer of living tissue, the photon's physical journey ends. When it strikes a photoreceptor cell, it triggers an electrical signal that travels through the optic nerve to the brain. In that instant, the long cosmic journey becomes perception. All the immense processes that began in the sun's core, fusion, radiation, convection, and the silent crossing of space, culminate in that delicate moment when the brain interprets light as an image. The brightness of the world around you is the final chapter of a journey that began in the heart of a star. It is remarkable to realize that every color we see, every outline of a mountain or leaf, every reflection of light in someone's eyes is simply sunlight completing its journey. The world itself becomes a mirror of solar history. Light leaves the star, touches the Earth, and is transformed into vision, warmth, and life. When we imagine the photon finally reaching the retina, there is a quiet sense of completion. After an eternity of collisions and centuries of wandering inside the sun, it fulfills its purpose in a fraction of a second. It disappears into our perception so that we can understand the world around us. Sunlight, in this way, is not just illumination. It is a bridge connecting the nuclear heart of a distant star to the fragile biology of human consciousness. Every ray of light that reaches us carries the memory of a cosmic journey, and when we close our eyes and feel the warmth on our eyelids, we are sensing the end of a voyage that began long before we were ever here. After following the heroic and persistent journey of the photon, from its birth within the crushing depths of the solar core to the instant it touches our perception, we arrive at the moment to understand how this invisible force shapes every pulse of life on our planet. Can you imagine what Earth would be like if the sun, even for a brief moment, decided to silence its radiant flow? What we perceive as light and warmth is, in reality, the primary energy that sustains the intricate web of life and maintains the dynamic balance of our entire planetary system. To understand this impact, imagine Earth not as an isolated object drifting in the vacuum, but as a living organism that breathes and feeds from its parent star. The Sun acts as the grand conductor of an invisible orchestra, where every biological and geological process follows the rhythm dictated by nuclear fusion occurring 150 million kilometers away. One of the most fascinating consequences of this energy appears in the quiet transformation taking place in every patch of green covering our world. Let us imagine descending into the delicate cellular structure of a leaf, where photons that have just completed their 8-minute journey through space arrive with remarkable precision. Inside microscopic structures known as chloroplasts, sunlight becomes the driving force behind photosynthesis. Here, the energy of light breaks apart molecules of water and combines their components with carbon dioxide, forming glucose, the fundamental chemical fuel of life. It may seem astonishing to realize that every piece of food we eat, every piece of wood that burns, and every breath of oxygen entering our lungs is ultimately stored sunlight. Modern biochemistry provides clear evidence that life, as we know it, is a direct expression of solar generosity. In this quiet exchange, the physics of a star merges with the chemistry of living cells. Yet the influence of the Sun extends far beyond nourishment. It is also the engine behind the vast atmospheric movements that shape our climate. Imagine the Sun warming different regions of Earth unevenly. Near the equator, sunlight strikes more directly, heating the air and oceans more intensely than at the poles. This difference creates pressure gradients that set the atmosphere in motion, forming winds that travel across continents and oceans. The Sun, in this sense, acts like an enormous heat pump, lifting warm air upward in tropical regions while cooler air descends elsewhere, circulating energy around the planet. Without this constant input of heat, the oceans would freeze solid, and the atmosphere would become a silent frozen shell around the planet. The delicate balance of temperature on Earth depends strongly on another invisible ally, our atmosphere. This thin envelope of gases serves both as shield and blanket. It protects us from harmful ultraviolet radiation while allowing visible light to pass through. At the same time, gases such as water vapor and carbon dioxide trap a portion of the heat radiated from Earth's surface, creating the natural greenhouse effect that keeps the planet comfortably warm. Without this protective layer, the average temperature on Earth would drop to about -30 degrees Celsius, turning our oceans into vast fields of ice. The gentle warmth we feel each day exists because sunlight and atmospheric physics perform a careful dance of absorption, reflection, and retention. Another remarkable system powered by solar energy is the water cycle. Every cloud drifting across the sky, every drop of rain falling onto a forest or river, begins its story in the warmth of sunlight striking the oceans. Solar heat lifts enormous quantities of water vapor into the atmosphere through evaporation. Carried by winds, this vapor travels across continents until it cools and condenses into clouds. Eventually, it returns to the surface as rain or snow, replenishing rivers, lakes, and groundwater. The Sun performs this immense task tirelessly, evaporating trillions of tons of water every single day. Without that steady supply of solar energy, the rivers would stop flowing and life on land would struggle to survive. Beyond Earth's atmosphere and oceans, the Sun also protects the entire solar system through its magnetic influence and the continuous flow of charged particles known as the solar wind. This wind expands outward in all directions, creating a vast protective bubble called the heliosphere. Within this bubble, much of the dangerous cosmic radiation from distant parts of the galaxy is deflected away. When some of these solar particles interact with Earth's magnetic field, they produce one of the most beautiful natural displays on our planet, the auroras. These shimmering curtains of green, red, and violet light near the polar regions are a visible reminder of the Sun's magnetic breath reaching across space. Solar energy also quietly shapes the rhythms of our own biology. The cycle of day and night regulates what scientists call the circadian rhythm, the internal clock that governs sleep, hormone production, body temperature, and even mood. Human physiology evolved under the steady pattern of sunlight and darkness created by Earth's rotation. Our bodies respond to the presence of morning light by adjusting hormones and alertness, while darkness signals the approach of rest. Even the production of vitamin D in our skin depends on solar radiation. In many ways, We are biological instruments tuned to the rhythm of our star. On a grander scale, the sun's immense gravity holds the entire solar system together. Earth remains in a stable orbit at just the right distance, what astronomers call the habitable zone, where temperatures allow liquid water to exist. Too close to the sun, and our oceans would evaporate. Too far away, and they would freeze. This delicate orbital balance has persisted for more than 4.5 billion years, giving life the time it needed to emerge, evolve, and flourish. The stability of this arrangement is one of the quiet miracles of celestial mechanics. Looking toward the future, the sun will continue to be the central source of energy sustaining life and shaping our environment. Every sunrise we witness is a continuation of the same nuclear processes that began billions of years ago in the depths of a molecular cloud. The warmth on our skin, the winds across the oceans, the growth of forests and crops, all are expressions of the same stellar engine. Reflecting on this influence invites a sense of humility. The sun does not choose where to shine or whom to nourish. It simply radiates energy in all directions, following the unchanging laws of physics. Yet within that steady outpouring, an entire world has flourished. Every breath we take, every drop of rain, every green leaf reaching toward the sky carries the signature of sunlight. Now that we have felt the depth of this relationship between our planet and its star, we can gently turn our attention to the distant future. Like all things in the universe, the sun itself follows a life cycle that will eventually lead to transformation. The light that sustains us today is only one chapter in a much longer story, a story that stretches billions of years forward into the quiet evolution of our star. We now arrive at the final stage of our long journey, the moment when we leave behind the present and the past to gently look toward the distant future of our star. Can you imagine what happens to a giant like the sun when it finally begins to exhaust the fuel that has sustained it for billions of years? Speaking about the end of the sun is not a story of catastrophe, but rather the graceful conclusion of one of the universe's most remarkable natural processes. Everything that is born in the cosmos follows a cycle, and the sun is no exception. Today it lives in its mature and stable phase, known as the main sequence, but the same laws of physics that ignited its light also determine how that light will one day transform. In roughly 5 billion years, the supply of hydrogen in the sun's core will begin to diminish. You can almost feel the subtle tension of that moment. Without enough hydrogen to sustain fusion in the center, the outward pressure produced by nuclear reactions will weaken. Gravity, which has patiently pressed inward since the beginning, will once again take the lead. The core will begin to contract under its own weight, becoming hotter and denser as it is compressed. But this contraction will ignite a new process in the layers surrounding the core. Hydrogen that still exists outside the center will begin to fuse in a shell around the collapsing core. As this shell of fusion intensifies, enormous amounts of energy will push the outer layers of the sun outward. Slowly, our familiar yellow star will begin to swell. Over millions of years, the sun will grow into what astronomers call a red giant. It will expand hundreds of times beyond its current size, its surface cooling slightly as it stretches outward, giving the star a deep reddish glow. Imagine looking up at the sky during that distant era. The sun would no longer appear as the modest disk we see today. It would dominate the sky with a vast and luminous presence. In this expanded state, the sun will engulf the inner planets. Mercury and Venus will almost certainly disappear inside the swollen stellar atmosphere. The fate of Earth remains uncertain, but even if our planet escapes being swallowed, the intense heat will evaporate the oceans and strip away the atmosphere long before that moment arrives. Yet deep inside the contracting core, another dramatic transformation will occur. As gravity continues compressing the core, the temperature will eventually rise to nearly 100 million degrees Celsius. At that extraordinary threshold, helium nuclei will finally begin to fuse together. This event is known as the helium flash, a powerful burst of energy that briefly restores balance inside the star. Helium fusion will produce heavier elements such as carbon and oxygen, marking the final stage of nuclear burning for a star like the sun. For a time, the sun will find a new temporary equilibrium, quietly converting helium into heavier elements. But this phase will not last nearly as long as the billions of years spent burning hydrogen. Eventually, the helium fuel will also be exhausted. Without new reactions to support it, the sun will become unstable. The outer layers will begin to pulse and drift away into space, During this period, the sun will release vast shells of glowing gas, expanding outward into the darkness. These clouds will form what astronomers call a planetary nebula. Despite the name, these structures have nothing to do with planets. They are delicate and luminous envelopes of gas, illuminated by the remaining heat of the dying star at their center. It is difficult not to feel a sense of quiet beauty when imagining this stage. The sun will be returning its material back to the galaxy, releasing the elements forged during its lifetime. Carbon, oxygen, and other atoms created in its core will drift outward into interstellar space. Over immense spans of time, those elements may become part of new molecular clouds, new stars, new planets, and perhaps even new forms of life. At the center of this expanding nebula, the remnant of the sun will remain, a small, incredibly dense object known as a white dwarf. Though it will contain nearly half the mass the sun once had, it will be compressed into a sphere roughly the size of Earth. In this strange state of matter, gravity is balanced not by nuclear fusion, but by a quantum mechanical effect known as electron degeneracy pressure. Electrons resist being squeezed into the same quantum states, and this resistance prevents the core from collapsing further. The white dwarf will shine at first with an intense bluish-white glow, radiating the leftover heat accumulated during billions of years of fusion. But no new nuclear reactions will occur inside it. Over unimaginable stretches of time, trillions of years, it will slowly cool, fading gradually into darkness. By that time, the solar system will have changed beyond recognition. The planets that once orbited a bright yellow star will circle a dim stellar ember. Yet the sun's legacy will remain scattered throughout space. The atoms it forged will travel across the galaxy, contributing to the ongoing cycle of cosmic creation. When we reflect on this distant future, it invites a sense of calm rather than fear. We are living during the stable middle age of our star, in a moment when the sun shines steadily and generously. The light warming our world today is part of a process that began billions of years ago and will continue for billions more. In this perspective, our own existence becomes a brief and luminous moment within a much larger cosmic rhythm. We are observers living during a quiet chapter of the sun's life, able to understand the processes that shape stars and the universe itself. As we reach the end of this long and quiet journey, we return to the present moment with a deeper awareness of the star that illuminates our world. Throughout this exploration, we followed the sun from its earliest beginnings inside a drifting molecular cloud, watched gravity gather the raw ingredients of a star, and felt the ignition of nuclear fusion deep within its hidden core. We traced the patient path of energy as it struggled through layers of dense plasma, witnessed the restless motion of convection, and followed a single photon as it finally escaped into space and crossed the vast distance to reach Earth. And when that light arrives here, touching the oceans, the forests, and our own skin, it becomes far more than radiation traveling through space. It becomes warmth. It becomes wind. It becomes the quiet chemistry that allows plants to grow and breathe life into the atmosphere. The sun's energy circulates through every corner of our world, shaping weather, guiding the rhythms of living organisms, and sustaining the fragile balance that makes Earth a home. In many ways, the sun is the silent architect of our daily existence. Each sunrise is not simply the beginning of another day. It is the continuation of a process that began billions of years ago in the depths of a collapsing cloud of gas and dust. The light entering your window this morning carries within it the history of nuclear reactions that occurred long before human civilization ever existed. When we pause to reflect on this connection, something remarkable becomes clear. The sun is not distant from us in any meaningful sense. Its energy flows continuously through our atmosphere, our ecosystems, and even through our own biology. The oxygen we breathe, the food we eat, and the warmth that regulates our climate are all expressions of that steady stellar engine. And yet the sun itself is also part of a larger cosmic story. One day, far in the future, it will expand into a red giant, release its outer layers into space, and leave behind a quiet white dwarf, slowly cooling in the darkness. The same star that now sustains life will eventually return its matter to the galaxy, allowing new stars and worlds to form. In this way, the sun participates in the great cycle of transformation that shapes the universe. This understanding reminds us that existence is not static. Everything evolves, from atoms to stars to galaxies. The light we see today is part of a process that stretches across unimaginable spans of time, linking the past, present, and future through the laws of physics. And in the middle of that vast timeline, there is this brief and beautiful moment in which we are able to observe it. We live during a calm chapter in the life of our star. The sun is stable, radiant, and generous, providing a steady flow of energy that allows oceans to move, forests to grow, and minds like ours to wonder about the universe. So the next time sunlight touches your face, you might remember the extraordinary journey behind it. A journey that began deep in the core of a star, traveled patiently through layers of plasma, crossed the silence of space, and finally reached your world. It is a quiet reminder that the universe is not only vast but deeply interconnected. And as we let these thoughts settle, allowing the calm rhythm of science and the cosmos to slow the mind, we can rest with the comforting knowledge that above us shines a star whose light has guided life on Earth for billions of years. If you enjoy calm explorations of astronomy like this one, you're warmly invited to subscribe and continue discovering the quiet wonders of the universe here on Cosmos for Rest. Your support helps this space remain a place for peaceful learning, reflection, and curiosity about the cosmos. Now let the mind grow quiet, let the vastness of the universe gently fade into the background, and allow the steady glow of the sun to carry you into rest.